Today we're going to relate bond enthalpies to bond strength and use bond enthalpies to estimate delta H for reactions. So we're getting into a little bit of thermo again. Rank and justify the ranking of bond polarity on the basis, there's a typo there, sorry, on the basis of the locations of the bonded atoms in the periodic table. All right, so through those things we're going to also talk about a little bit of dipole moments and some molecule polarity before we've talked about bond polarity. Now we're going to look at molecule polarity. This goes well with Lewis structures B. So bond order. Bond order is simply the number of bonding electron pairs that are shared by two atoms in a molecule. So bond order is pretty straightforward until you get into resonance. When you only have a sigma bond, that's a single bond, between two bonded atoms, the bond order is 1. When you have two shared pairs between two atoms, one that's a sigma and one that's a pi bond, so in other words a double bond, your bond order is 2. And then when you have 3 shared pairs between two atoms, one that's sigma and 2 that are pi, that's a triple bond, your bond order is 3. Fractional resonance is when you have something with a resonance structure. So say fractional bond order, we've talked about ozone before. We know this is one of the resonance structures for ozone. We also know the other one looks the same, just with the double bond on the opposite side. If you count up the number of shared pairs there with the central oxygen and divide it by the number of things it's bonded to, you get a fractional bond order. So we see that we have 3 bonds. We have 2 single bonds, and then we have the double part of that double bond. So 3 total. It's bonded to 2 things, and that's how we get our fractional of 3/2 or 1.5. When we think about formal charge, that also makes sense. We may have seen that formal charge before where the positive, it was a positive and negative on there. Really, that charge is shared over the whole molecule when you're looking at ozone in this context with the dashes. So bond order is important when it comes to looking at how strong the bonds are. We know that the higher the bond order, typically the stronger the bond. All right, so we can see here that relationship between bond order, bond enthalpy, and bond length. Here we've got a carbon single bond to an oxygen, a carbon double bond to an oxygen, and a carbon triple bond to an oxygen. As you see, the length gets smaller as we have more electron density. Those things get pulled closer together. When in terms of the bond enthalpy, if we were to compare the bond enthalpy, so that would be our delta H, we would get that from a table, and we would look at that table a little later. We know that it is about 358 kilojoules per mole to break a carbon single bond to an O, and it's about double that for carbon double bond. And then if I look at my table, I believe carbon triple bond is 1072. So it does go up significantly when you start to have a double and a triple bond. Double bonds are not quite double that of a single bond. It's easier to break a pi bond itself. So when we talk about bonding a little bit more and the geometries, we have pi bonds and sigma bonds. A sigma, so this is sigma, it's the same as a single bond. And then we have a pi bond. This is the same as the double part of the double bond. So when I'm referring to pi, so here would be, say this is our single bond. This would be a sigma, and when I'm sigma, and when I'm looking at the double bond, Oop. One of these is the sigma. The other line is the pi bond. When we think about orbitals and how they overlap a little bit later, that'll make a little bit more sense. So when we're looking at a triple bond is really 2 pi and 1 sigma bond. And that is actually something that we covered back here. So that's where we're getting the 1 sigma and 1 pi for a double bond, and then 2 pi and 1 sigma for a triple bond. Okay, but pi bonds are typically a little bit weaker than a sigma bond. It's just when we go to break a double bond, we've got the combination of a sigma and a pi. When we go to break a triple bond, we've got the combination of a sigma and 2 pi bonds. So it's a little bit harder to break the attraction of both. All right. So with this table, we're going to be able to look at the breaking of bonds and the forming of new bonds. An important concept here when it comes to bond energy and bond association energy, breaking bonds is endothermic. It takes energy. Forming bonds is exo and releases energy. And by forming bonds, we're putting ourselves at a lower energy state, and therefore energy is released. We covered that in the thermo unit. It's been a while. I just wanted to remind you of that. In terms of these, with covalent molecules, these numbers that you're seeing in this chart here, we're going to treat these as positives for the entire time for this unit. We know before that we do products minus reactants. We're not necessarily going to do that here. When we calculate delta H for a reaction for these types of problems, we're going to look at the sum of the energy for the bonds broken minus the sum of the energy for the bonds made. So the nice thing is you don't have to look at any of the positive or negative charges. You don't have to think in terms of positive or negative. Just know that your answer, if it's more thermodynamically favorable, your answer at the end will be negative because it's exothermic. If it's not as thermodynamically favorable, which means you're breaking way more bonds than you're forming, you're going to be endothermic. Okay? So here's an example. Calculate delta H for the reaction of methane with chlorine and fluorine to give freon. So the best way to attempt this problem, and I know it was difficult back when we did it in thermo because we hadn't looked at Lewis structures in a while, but you got to be able to draw Lewis structures. I would go through, draw all of the Lewis structures. That's the first step. So methane, and I've got 1 methane. I've got 2 chlorines, which are single bonds. Oop. I've got 2 fluorine molecules if I look at my balance. And then on my product side, so these are the bonds that I'm forming. I'm going to be forming 2 CF bonds and 2 Cl bonds. I'm going to be forming 2 HF bonds. Oop. So HF and HF. And I'm going to be forming 2 HCl bonds. Okay. So now that I can see what I'm breaking, what I'm forming, I need to refer to my table. So I'm going to set this up. I'm going to say I'm breaking 4 times whatever my HCl is. Or sorry, not HCl, my HC. I'm breaking 4 carbon HC bonds. I am going to break 2 chlorine-chlorine bonds, and I'm going to do 2 times my fluorine-fluorine bonds. Okay, and then from that I'm going to subtract the 2 carbon-fluorine bonds, the 2 times carbon-chlorine bonds, the 2 times the HF bond, and the 2 times HCl bond. Okay. So when I put all those numbers together, all right, so I've got 4 times CH, so I've got 4 times 413. I've got 2 times ClCl, which is here. It's 239. Oops. 2 times 239 plus 2 times fluorine. Fluorine is 154. Okay, close parentheses, and then I've got 2 times my carbon-fluorine bond, which is 485, plus 2 times carbon Cl, which is 339. Oops. And then 2 times my HF bond. 2 times HF is 565, and then 427 for HCl. When I say 565 and 427. 565 and 2 times 427. Okay, I'm going to need a calculator for it. So let me pull up my calculator. Let's bring that up here. Nice. So on one side I've got 4 times 413 plus 2 times 239 plus 2 times 154. And then I'm going to close parentheses again, and then 2 times 45 plus 2 times 339 plus 339, typo there. Okay, and then 2 times 565 and 2 times 427. All right, and I'm going to get a total of negative 1,194 kilojoules per mole as my delta H. Is this exothermic or endothermic? It's exothermic. We are definitely giving off energy. We're forming way more bonds than we are breaking. Okay? Or rather, we're forming way more favorable bonds than we are breaking. All right, let's do another one. Do this one on your own. CH4Cl2, and you get CH3Cl, HCl as your products. So go ahead and calculate this one on your own. All right, if I draw my Lewis structures, I know I've got 4 CH bonds I'm going to have to break, and I've got 1 Cl-Cl bond that I know I'm going to have to break, and I know I'm going to end up forming 1 CCl bond, and 3 CH bonds, and then an HCl bond. Okay, so products, or sorry, bonds broken minus bonds formed, so 4 times 413 plus your ClCl, which is 339. All right, minus 3 times 413 plus 427 for the HCl and plus 339 for the ClCl, or CCC, carbon fluorine bond. Okay, and I end up getting a negative 14 kilojoules per mole. It is exothermic, but just by a little. Now, you'll notice that here, 3 of these bonds technically stay the same, and when I do my calculations, they actually account for each other and they cancel out. So do you really need to worry about that when you're doing that math? Not necessarily, but oh, I'm sorry. I had a slight math error. This should be 239 for chlorine. That's down here. 239, not 339. All right, but the 3 times 413, technically you don't need that in your calculation because those 3 bonds stay the same. But just to make sure everything works out, you should double check that. Okay, so this is actually negative 114 kilojoules. I'm sorry. But still should work out the same. All right. So the last thing we're going to cover today is looking at a dipole moment. All a dipole moment is the unevenness of electron distribution across a bond due to unequal sharing. This happens when you have a component of your molecule that is more electronegative than some of the other atoms in that molecule. So you get uneven sharing and an increase in electronegativity difference that would cause you then to have a dipole moment. So I'm going to go back to full screen with this. Can I get rid of the calculator? Yes, I can. All right, there we go. Before we even really get into this, I want to look at the Phet simulation because it actually is a pretty good job. Oh, the real molecules isn't available in HTML5. That's fine. Okay, so when you're here, there's a couple of things I want to look at. There is bond character, which tells you if it's more ionic or more covalent. There's bond dipole, and then there's partial charges, and all of those things are good to see. I also like having electrostatic potential on here. And why not have an electric field too? So the cool thing about this is this thing here is kind of in the middle. It's not quite ionic, it's not quite covalent, but it is polar. You see this dipole, there is an uneven distribution of electrons here, and you'll see that even if I try to turn this molecule around, it always turns back around when it's in an electric field. That's how we know it's polar, because there's an uneven distribution. When there's an uneven distribution, we get a partial negative and a partial positive on the two sides of your molecule. And when that happens, they will be attracted by opposite ends in a magnetic field. If I was to increase the electronegativity of one, you see that the bond character is getting more and more ionic, and your dipole, which is that arrow, is getting bigger. Also, the colors for the electrostatic potential are getting more vibrant, meaning that there's more density of electrons there. So red is higher electron density, blue is less electron density. If I try to turn this thing around, it goes back a lot faster. Whereas here, if I try to turn it around, it's kind of slow. And in here, where I'm nonpolar, I can turn myself around and nothing happens. I just kind of hang out there. If I increase myself a little bit, you see I start to orient, and very slowly I start to move back towards my poles. And if I were to increase this a little bit more, see, make myself a little bit more, see, it goes faster and faster. And then, when I have a very large difference there, that is when you see that change in the orientation due to the magnetic field. Now, if both of my atoms were really electronegative, you can be really electronegative and be a nonpolar substance. And you could look at chlorine gas or fluorine gas. We know that both of those atoms are really electronegative, but they pull on each other equally, like tug of war. It's also important to look at this too in terms of three atoms. If I had three atoms, and let's say I have minimal electronegativity here between all of them. It's nonpolar, it doesn't really do much, whatever. The minute I start to increase the electronegativity of my central atom, I get a net dipole. I get a dipole from C towards B and a dipole from A towards B. And overall, that gives me a net dipole, which is my molecule dipole, the one in yellow. And as I increase that thing, this molecule becomes more and more polar. And same deal as we saw before. The greater the difference, the faster it responds in a magnetic field. I can even change my dipole so that it's more towards one end. I could have it where, let's say I had like this. Say carbon, or not carbon, say C was really, really electronegative, and my net dipole would be pointing towards that. Or I could have something like this, where I have a complete split where I've got a partial positive and a partial negative on each side, but they pull on each other in equal and opposite directions, and they cancel out. Now with this one, it's really hard to see. The more I change that angle, the more I get more of a dipole. But when I have almost a perfect distribution here, it doesn't really respond to the polar ends of the magnetic field. You see that the dipoles cancel each other out because they're in equal and opposite direction, and then there's no molecular dipole. So that's really important. You can have polar bonds, but not be a polar molecule if your geometry allows you to pull in equal and opposite directions. Okay, so if we look at something like methane, methane is non-polar. One, we know those bonds are not polar, and two, we know that they pull in equal and opposite directions anyway, and they would all cancel out. So we have two criteria. One is that you need to have polar bonds, and two, you need to be an asymmetrical molecule. When I'm talking asymmetrical, you need to have at least two lines of symmetry here. When we're looking at things in 3D space, it'll be easier to see. Here we've got two lines of symmetry. It's going to be non-polar. But the minute you start throwing on some electronegative groups on there, you're going to make your molecule polar. So here I throw on a chlorine, which is electronegative. We're going to get a dipole that goes towards this end of the molecule. Definitely going to be polar. You could even add on another chlorine group. Say we had like this. And while we may be symmetrical in one direction, we're not symmetrical in the other direction. So overall, we're going to get a dipole this way. Even when we have three of them, it's still going to be pretty polar. Everything's going to be shifted with a net this direction. These are all polar. What about this last one, CCl4? This one's tricky. Because CCl4, now we've got something that's symmetrical. You have polar bonds, that's for sure. But this is one of those cases where you've got pull in all four directions, and they will cancel each other out. And you'll have a non-polar molecule, even though you have polar bonds. Okay? We'll do a little bit more practice with that once we get to the hybridization and bonding of molecule geometry, and it will hopefully make a little bit more sense then when we see it in 3D space. All right, that is all for today.